Thank you very much, and thanks for inviting me to give a talk. First, I have to confess, I'm not applied, I'm not computational, and then I'm even not topologist, so I have to excuse for my existence. I'm coming from stochastics, and we are working in stochastic geometry, our group in Osnabrück, and I want to show you how far we got when we were interested in random geometric graphs and random simplicial complexes. It's somehow one part is about the method and what we can do with this method and where it leads us to. And the second part is about applying this method to random geometric graphs and what it means for that. So the introduction is something which every one of you knows. We start with a Poisson point process of a certain intensity T, which means that the underlying measure is the Lebesgue measure in the whole space, and T is just how many points we expect in a set of volume 1. And this just means that if I have such a window of a certain volume, then I see several points, and the number of points is Poisson distributed with parameter T times this volume. And if we have two windows, W1 and W2, which are disjoint, then we have independent random variables. So this is the classical model. And what we are interested, or we have been interested in stochastic geometry, is we start with a Poisson point process, and then around each point we draw a ball of a certain radius. This gives the so-called Boolean model in stochastic geometry, and we wanted to study this Boolean model. And there are classical questions which are well understood. This is, what is the volume which is covered? What is the surface area of this thing? What are the intrinsic volumes of this in expectation? And then the next step some years ago was, can we understand the topology of the outcome of this Boolean model? And for the topology, it suffices to know about what you call the nerve of this thing. So each time two of the circles overlap, we just draw an edge between them, and this gives us a certain random graph. And this is the random geometric graph, or the Gilbert graph, or the distance graph, or there are several names for that, and we want to understand how this graph looks like. And this is a very thin graph because our balls have been somehow small, and it's clear if you increase the ball size, then you get more and more edges for that.
You don't add any synthesis, you just record like two things.
Yes. In the first step, we are only interested in the graph. Yes, and in maybe 15 minutes, I will add some synthesis. It will come. But say in the classical part of this talk, we were just interested in the graph itself. So we have a certain a graph given by a certain number of vertices and the number of edges, and the vertices are just all points of a Poisson point process, and the edges are just all connections between 2 points if the distance between 2 points is bounded by a certain parameter, which is called delta. And the small t by the Poisson point process, eta t and delta t, means that we have an underlying intensity t for the Poisson point process, and the delta also depends on this t. And then one is interested in the number, so the first trivial or more or less immediate questions are number of edges and and the total edge length. So the number of vertices is clear, this is Poisson distributed. Number of edges and total edge length means you just take all pairs, and this is what I denote by eta t squared and not equal. And I count how many of these pairs are there which are bounded by, where the distance is bounded by delta t, and for the total edge length, we just multiply by the length of the edge. And if I write it in this way, it's immediate that this is always infinite. Because I have infinitely many points, and this gives me infinitely many edges in general, and so to make it a senseful question, we have to intersect it with a certain bounded region, and this is what I call a window W. So I take all points in my window W, and then I ask the same question. And throughout the next half of an hour, I will always assume that we have restricted it to a certain window, and at the very end of my talk, I will come back to the whole space and the whole question. Okay, this was I think, in several papers investigated, and then was a seminal book by Matthew Penrose, and he was interested how these things look like, and I think the main goal in the book of Matthew Penrose was to prove central limit theorems, and he could prove that the number of edges in such a window is normally distributed if the intensity tends to infinity. And I don't want to be precise, there are certain regimes, but he was interested in the regimes where you really see the central limit theorem. And in the same way, he was interested in the central limit theorem for the total edge length. And he proved central limit theorem using Stein's method, but somehow he didn't take care of giving the deviation between this distribution and the normal distribution. So it's somehow implicit in his book, but he didn't make it explicit. So when we started some years ago, we observed that we are close to a very classical thing. So if we would start with a fixed number of points in a window, then the number of edges would be a U statistics. And this is the classical notion of U statistics. Each one of you has heard in his talk in probability theory. So you have random variables set 1 up to set n. And the U statistic is just you have a certain function f, which is the kernel of the U statistic. You take all k tuples, develop f of the k tuple, and then you sum over all k tuples. And in the classical notion, you would have to normalize that. You have n random variables, you have k tuples, so you have n over k summands, and then you divide by n over k to make to have the correct normalization for that. Now, we didn't start with a fixed number of points. We started with a Poisson point process, and so we introduced Poisson U statistics, which means you have a Poisson point process, you have a certain kernel f, and now you take all points of your Poisson point process, or all k tuples of points of the Poisson point process, you calculate f of this k tuple, and you sum over all k tuples of the Poisson point process. This looks like a U statistic as before, but there's one major difference. In the classical sense, you know how many summands are there, n over k, so you are able to normalize. And the number of summands is always bounded. Here you don't know how many summands you have, because the number of points is a random variable, so you have a random number of summands. It's not possible really to normalize that. And even in many interesting cases, you will have infinitely many summands. Yeah? So you from the very beginning, you have an additional task which you didn't have in the classical question, namely, is this convergent? Convergent, and in which sense this is convergent? Yeah? Now, a first step, yeah?
Why can't you normalize using the expected number of vertices?
Assume that your Poisson point process lives on the whole space, you have infinitely many points.
But if you did it in a window, what is
Then you could take the expectation, yes.
Is that done?
You can normalize by any constant, but in most cases you can just calculate that, and at the very end you see how this thing depends on the intensity. And the natural guess is the intensity is t to the power k, because you have all k tuples, and then you have to normalize by t over k. Yeah? Yes, you can do that, but there's no simple way, I want to say. Yes, in the classical way, there's a simple way because you know how many summands here, you don't have that. Yeah? Okay, first answer to the question of convergence. You take the expectation of this thing. So you want to know whether capital F, your U statistic, is in L1. Yeah? So you have to take the expectation of this sum, which maybe is infinite. But then there's something which is very nice, the so-called Slivniak-Mecke formula, which tells you if you have the expectation of such a U statistic, then the expectation of the sum is just the integration. So you can replace expectation of sum just by an integral. And you have to integrate the kernel with respect to the intensity measure of the Poisson point process. And this tells you if this integral is finite, then your capital F is in L1 and otherwise not. And it gives you a more or less simple way to really compute the expectation of all these functionals. Yeah, you take the kernel and just integrate it over the space you're interested in, over your window if you like, or over the whole space. And this means that computing the expectation is somehow a classical task in these questions. Okay, I don't want to go further. The question when this is in L2 or even L infinity turns out to be really complicated. For example, I just want to mention if the kernel f is in L2, this will not suffice to make your capital F the U statistic in L2. There are counterexamples to that. And the other way around, it is not sufficient that capital F is in L2 to force the kernel, small f, to be in L2. So it's really a complicated connection between the kernel and the capital F. Okay, I will switch to say a very theoretical tool, which is the Maleveux calcul for functions of a Poisson point process, and I just want to mention it how it works, and to show you one or two ingredients for that which are essential for what we are doing. So I have such a function of a Poisson point process, and now I assume from the very beginning that this function is in L2. It's not necessarily a Poisson U statistic or something like that. It's just a general functional of a Poisson point process. Then there's the so-called Wiener-Ito-Cars expansion, which guarantees us that such a functional can always be decomposed in something which I call a random Fourier series. So I have an infinite series here. And the nice thing is that this series is orthogonal, meaning that if you take two summands here and take the expectation of the product, this is always equal to 0, just like in a Fourier series. Yeah? For example, if you square this thing and take the expectation, then all mixed summands will vanish if you take the expectation. Yeah? So I have a really nice orthogonal random series for that. The question is, can we compute this thing? So we have the capital F, and we want a nice, simple, and in my field of work, we want a geometric way to compute this series here.
What are the i's here?
The capital I and the small f are not defined, and I will define it in the next two slides. First, we start with the small f. Yeah? And for this, it's important to introduce the difference operator. So I have my functional capital F, and then to my Poisson point process eta, I add an additional point y, yeah, which is not random. And I measure the effect of adding this point y. So I have f of eta plus y minus f of eta. This is what we call the difference operator at one cost operator. So this depends now on y and on the Poisson point process eta, and I take the expectation with respect to eta. And after taking the expectation, it depends only on y1, and this is the first derivative. So something like a directional derivative with respect to y1, direction y1. And we really call this some kind of derivative. And now we continue this process. This is the first derivative, and now we compute the second and the third and so on, and always we take, so the definition is clear. We have more and more points which we add, and we compute this add cost one operator iteratedly, and then it depends here on y1 up to yi and on eta, and we take the expectation with respect to eta. So at the very end, I get a derivative, a discrete derivative, depending on I points y1 up to yi. And this is what we call the kernels of the Wiener-Ito-Cars expansion. This turned out to be extremely useful because when we're working in geometry and in the background we have, say, this random geometric graph, what we have to do is we add one single additional point. And we're looking for the influence. Yeah? And this is something which can be computed. And then we take the expectation, which is also simple. So this is some tool which is not very, there's some theory behind, but in geometry you have a possibility to compute the things really afterwards. And now capital I. What you are doing now is you have first differentiated, now you integrate back. And you integrate back with an additional Poisson point process. So you started with a Poisson point process, you had these additional points, then you take the expectation with respect to a Poisson point process, so the Poisson point process was removed, and now you introduce it again because you integrate with respect to the compensated Poisson point process here. I don't want to be very precise, this is the E2 integral here. Yeah?
Your diagram there, is that
Any.
Completely static.
Any.
Any.
Any, yes. So in most cases, if you have something like absolutely continuous, no, forget it. So yes, you really need I tuples. So really different. Sorry? Distinct I tuples. Yes, yeah. There's a very nice feature of this Wiener-Ito integral. This is the isometry property. If I want to know what is the expectation of the square, so the second moment of such a Wiener-Ito integral, then we can ignore the integration here and just take this kernel Fn and take the 2 norm of this Fn. This is the same as the 2 norm of this Wiener-Ito integral. This gives us somehow a simple way to compute the second moments. Okay, this was some kind of general theory behind the whole thing. And now we are interested in this Poisson U statistic. So we start with a very special function, capital F. Capital F consists of a sum of all k tuples. And the number k is finite. And then it turns out if you add here one additional point, then most of the summands will not have this additional point. So they will cancel out. So you only end up with with a certain small sum. And this can be continued, and we can make very precise how these derivatives look like. And the derivatives are given by, so the ith derivative means you fix I point in your kernel, and the other k minus I point are just integrated. So this derivative, this discrete derivative, is somehow connected in a more or less nice way to integration with respect to the underlying measure. And then you have to integrate it again, okay. Which means, and this is the point which the concrete formula is not so the point here, but we can really make it precise in all cases we're interested in. We can write down how this thing looks like. And this is nice. And the main observation was the following. If I start with a Poisson U statistic, and I compute this whole infinite random series expansion, then it turns out that this is always a finite expansion. It goes from I equal to 1, from 0 to k, and it vanishes starting with k plus 1. Which means now I have only a finite sum, and this helps me a lot with respect to convergence questions. Because now more or less we can really compute first and second moments by just computing the moments of this of I of Fi. And this is in both directions. So if I have a Poisson U statistic, this is finite. If this is finite, I have a sum of Poisson U statistics. Okay, now we've developed that to get something we were interested in, and we were mainly interested in the first step in a central limit theorem for such Poisson U statistics. And then it turned out that the very useful tool is using Stein's method, and there was I would say a very basic central limit theorem to Beccati, Sole, Uzet, and Taku. And we could take this for U statistics, and then we could prove a central limit theorem for U statistics of order k. So we fix the order k, and we want to know how far is our U statistic away from the normal distribution. And the nice thing is that we get precise upper bounds, and up to the constant, these upper bounds are really optimal. And I have to explain how to compute these things. So the expectation of f I have already shown. This is this Livniak-Mecke formula, which gives you a precise integral formula for your expectation. The next step is you have something to say about the variance. But if we go back to this thing here, we have the variance is more or less the second moment here. But if we square this and then take expectation, we know from the very beginning that all mixed terms cancel out, they vanish, because it's an orthogonal series expansion. So we only have the second moments of these summands here, which means we just have to know how these kernels here behave. And for these kernels, we have a precise description by integrations. Yeah? So we really have hands on this variance. And then the question is, what is, so k is clear, k to the 4k is then the order of the U statistic, and then M4. This is something We call it M4 because it's a mixed fourth moment, which means you take your function f, which is the kernel of your statistic, you write it 4 times. I was not very precise on this slide because it's too long then. And then you have m variables here, and you plug the m variables into these 4k places, and it must have a certain structure. So it's, for example, forbidden that x1 occurs on 2 places here and so on. Yeah? But in principle, this is something like a mixed fourth moment. And you have to compute this mixed fourth moment. And in most cases, we are interested in what happens is this mixed fourth moment is just a constant, and the variance tends to infinity, and then you see you have the bound is 2k4, which is constant, m4 is constant, you divide by the variance, this tends to 0. And you have really the upper bound you're interested in. At this point, I have to show you the, in my opinion, most aesthetic central limit theorem which is in this field at the moment. And this is the so-called fourth moment theorem from Lachesserie and Pecati. They could prove that a central limit theorem holds with a certain bound, and then the bound is just the deviation of the centered fourth moment to 3. Which means if you can prove that your fourth moment converges to 3, then you have a central limit theorem and you're not interested in higher moments. It just suffices to know what the fourth moment does. In principle, this is, in my opinion, the best one can write down. In practice, this is hard to use because you have to prove that something tends to 3, precisely 3, and this is hard. In many cases, it's simple to prove that something tends to 0. Maybe slowly, but it tends to 0. But that something tends precisely to 3 is I don't know any instance where one can use this theorem really to prove a central limit theorem. But from a theoretical point of view, this is for me, the most appealing form of a central limit theorem. You have to compute one moment, and you know whether the central limit theorem holds or not. Yeah? So I have to mention it, but somehow it turns out to be useless and no, for applications. Yeah? I really like the central limit theorem. And now there's much more. So in the last 5 years, there was an incredible research on this combination of Stein's method with the Maillard calcul and the Wiener-Ito series expansion. And I have listed some of the names who were involved in this field. Let's come back to the original question we have. We have this random geometric graph, we have our Boolean model, and we want to know how the edge length behaves. And now the very nice thing is that this is not even arbitrary U statistic. Clearly this is a U statistic. You check for all 2 tuples, are they sufficiently close or not? And that's the end. This is all what you have to do. But now you know that if they are sufficiently close, then it's fine. But if they are too far away, then nothing happens. So what you have is some kind of local U statistic. So a local U statistic is something where as soon as the points are too far away, then everything is vanishing. And this is what we have in our geometric random graph. This is true for the 2 tuples and also for the, say I will, in the next slides I will construct the Čech complex and the Vittori-Strip complex. It's quite clear if the diameter of the thing you're looking at is too big, then the things are not connected and everything is vanishing. So you really have a local U statistic. Everything vanishes if the diameter is too big. And for local U statistics, whatever this small f is, there's a central limit theorem, a general central limit theorem. So we have to assume that this first kernel, f1, which we have to compute, that this is positive and not vanishing. But if this is positive and not vanishing, then we know that the variance is of the order first kernel squared, and we know how the Wasserstein distance between the normal distribution and your pseudo normalized U statistic behaves. And here you see that the bound is a constant, more or less constant. It depends on your kernel small f. But in the intensity of the underlying Poisson process t, it's t to the power -1/2, and this is, in most cases, most instances, the best possible bound you can have. So this is really optimal in this sense. Yeah. And if you have this, then it's more or less immediate that you get for more or less for free all of your central limit theorems you're interested in. So for example, if you are just looking for the number of edges, then the number of edges is clearly a U statistic of order 2, and you get that a central limit theorem for this with a precise order t to the power minus 1/2, and you know how the variance behaves. It behaves like t. And here I have written that the dependence between delta t and t should be equal to 1, so you're somehow in the thermodynamic or critical regime. Let me go back. I have forgotten something. It might happen that f1 is equal to 0 and is vanishing. For this case, one also knows the limit behavior. So the theory goes through. You have to say in advance which of these kernels does not vanish, and the first kernel which does not vanish dictates what the limit behavior of this thing is. Yeah? But in most cases, the first kernel already is non-vanishing, and then you have a central limit theorem. And much more can be done in this sense. So, yeah, you can look for the length distribution or the squared length, and then, yes, several things. Okay, I wanted to say something about simplicial complexes, and the natural way now, if you have a random graph, is the Vietoris-Rips complex, which I think everyone here knows. So you connect 2 points if the balls intersect, and then you get a triangle, and because it's the Vietoris-Rips complex, you fill the triangle as soon as you have a complete graph. You take this as a face. And the Čech complex is more or less the same, but for each phase you have to check whether there's all of these balls intersect in a common point, or if there's a hole inside. So here's a hole inside. So you would take the 3 edges which form a triangle, but we would not take the triangle as a face. Yeah, and so it's quite clear that the k faces of the Čech complex are always contained in the set of k faces of the Vietoris-Rips complex. And in the following, I always will assume that my simplicial complex C is either the Čech complex or the Vietoris-Rips complex. And for all of these limit theorems, there's more or less no difference between these two. If you have a limit theorem for the one, then you get more or less immediately the limit theorem for the other. And the only differences are the constants which appear. So, we are not now no longer interested only in the number of edges, but we are interested in these simplicial complexes, and we want to know what is the number of k-dimensional faces, and the expectation is something simple. The number of k-dimensional faces is a local U statistic. For each k-tuple, we just check whether they are sufficiently close to form a k-face. This is a U statistic. The expectation is given by this Livignac-Mecke formula. This is classical, and I just don't write it down. Yeah? This is easy exercise to compute that. And we know that's a local Poisson statistic. If the points are too far away, they can't form a k-face. So we can just plug this into our question. We obtain a central limit theorem for the number of k-faces, again with an optimal dependence on t to the power minus 1/2, and this is in a thermodynamic regime. This was already contained in the book of Penrose without the rates of convergence, and now really well understood how this number of k-dimensional faces behaves. And even if there are limit theorems which are Poisson limit theorems and not central limit theorems. And this can be done in a much bigger generality. This also goes back or has its roots in the book of Penrose. You can ask for the set of subcomplexes, so you have, for certain subcomplex counts, if this calligraphic S is a set of subcomplexes, and with this I mean isomorphic versions, and we just count how often this subcomplex occurs in our Čech complex or Vietoris-Rips complex. Then again, this is a local U statistic. If you increase the diameter too much, it can no longer be connected, so everything should be equal to 0. For the expectation, it suffices to write down this Livignac-Mecke formula. Classically, you get an integration for that, and you see how it depends. And you know it's a local Poisson U statistic, and for free you get a central limit theorem. And now in this setting again with a rate of convergence, t to the power minus 1/2, it should be optimal. The next step would be the Betti numbers of the simplicial complex. This turns out to be much more complicated because the Betti numbers are no longer local U statistics. Yes, they do not fit into this framework. So the point is they are non-local. And we have seen in yesterday's talk how can deal with that. So the expectation and even the variance, you can write it down, again using this Livniak-Mecke formula. But now it turns out that these integrations are somehow ugly. So we don't know how, so say it this way, we can write down the integration. This gives us a very ugly integral representation. It is there, this is an explicit representation, but it's hard to see somehow what the constant in these things are. I think for the Betti number 0, there are certain expressions for the constants which can be attacked, but in general, the constants which appear here in this expectation are hard to understand and to write down. Nevertheless, even the book of Matthew Penrose, there were certain central limit theorems for the Betti numbers, and so in the book of Penrose, I think for beta 0, and then in the more recent papers by Kahle and Meckes, Bobrovsky, Skraber, Adler, and so on, they could prove that there are central limit theorems in certain regimes. So the Betti numbers are really well understood. Again, in most cases using Stein's method, but now no longer using this local U statistics because this does not fit into this framework. And much more. Laws of large numbers, Poisson limit theorem, so we had something about that already. What we have been interested in Osnabrück in the last year more now, are there concentration inequalities for all these things? So we know the expectations, we know central limit theorems. Can we prove that everything really is close to its expectation? And can we give more or less optimal upper and lower bounds in both directions? And this was done by Sascha Bachmann and Giovanni Peccati for the first 2 lines, and then joint paper with Sascha Bachmann for the last 2 lines. So we started with a nice local U statistic, and nice means that certain moments exist. I think the first moment must exist, and nice means that there should be certain upper and lower bounds for the kernel of the U statistic. And then we could prove that for all r greater or equal to 0, that we have an upper bound, that f deviates from its expectation by something. Okay, you have this thing here, and if you try to see how this behaves for r, then it turns out that this behaves like r squared. So you have e to the power minus r squared, which is what you expect by a central limit theorem. And for the lower bound, you have also e to the power minus r squared. So you get more or less optimal bounds for the deviation of the expectation. And the same works if you're interested in the median here. If you're interested in the deviation from the median, you have more or less something like r squared for the upper and for the lower bound. The method of proof is very different. So for the concentration about the expectation, they're proving a log-Sobolev inequality for functionals on Poisson spaces and then using the Herbst argument. And for the deviation from the median, there's a version of Talagrance's convex distance inequality, which can then be turned into a concentration inequality. So these are very general. For local U statistics, in particular, if you want to know concentration inequalities for the number of k faces, then we have precise bounds on the upper and lower bounds for this number of k faces. Around the expectation and median, and clearly expectation and median are very close and behave in the same way. And also, clearly, you cannot only count the number of k faces, but you can count all subcomplexes you're interested in, as long as they are connected. For the rest of my talk, it starts to be important that there are certain regimes for our simplicial complex. So we start with the random geometric graph, and we add the origin to our graph, and we ask to how many other points is this origin connected. And this is somehow the expected number of edges from the typical point. And as most of you will know, this depends on the intensity t times the radius delta t to the power d. And in the sparse regime, this should go to 0, which means that you see points, but the balls are so small that it's not connected to anything else. So you have you have more or less only isolated balls. Then in the thermodynamic regime, you always have that each point is more or less connected to a same number of points throughout the whole space. And in the dense regime, everything is connected more or less to everything. So every edge in the limit is, every vertex is connected to an infinite number of other vertices in the limit. So these are the two regimes. Sometimes the thermodynamic regime is called the critical regime. Just one slide about the percolation. You have a look at the component. So you add the origin and you look for the component which contains the origin, and then you just ask for the probability that this component is infinite, and this gives you a critical value here, which maybe most of you again will know. And this means graphically that if you increase the radius of your balls, then at a certain point everything starts to be connected, and you get an unbounded component in your random geometric graph. And this was made precise by Mester and Roy in the famous result that if you take your regime to be beyond a certain critical value, so you're in the thermodynamic regime or in the dense regime, and you are above this value Vc, which is the critical, then with probability 1, there's precisely one unbounded component. So if you're in the dense regime, you see only small balls, some, maybe 1 or 2 are connected, that's the end. Then you're coming to the thermodynamic regime, and at a certain point, suddenly there starts to be one big snake, and only one. And then if you increase further and further, this snake gets thicker and thicker, and it's something like a web, I don't know, yeah. So this is how the things look like. And then Sascha Bachmann was interested in the question, can we count the number of components with at most k vertices? And this is again something which can be done because this is something which is local. If you have at most k vertices, you cannot be too far away from each other, and you get a concentration inequality for component counts if you bound the number of vertices which are in this component from above. In the last year, we started to think about it once again, and the question was, think of the very sparse case. You only see very isolated points with small balls around it. More or less nothing touches each other, but you now have a look at the whole space. And then you take your favorite exotic space, some simplicial complex which is extremely complicated, which is huge, with a strange sequence of Betty numbers, whatever you think of. And then you ask, can you find this somewhere in your sparse scattered picture? Huh? So you have a big elephant, I don't know, and you're looking for that, but you only find single points isolated, and you're looking around. Is there a chance, given something like that, to find at least one, so that you find in the components of your simplicial complex at least one elephant? And the answer is yes, and you will not find one, you will find infinitely many with probability 1. Yeah? And the nice thing about this result is it's independent in which regime you are. You start with the big elephant you're looking for, you're in the very, very dense, very sparse regime. Nothing is connected, you're looking for your elephant. Maybe it takes you some time to find it, but you find it once, and then you find it again and again and again, infinitely often with probability 1, independent of how big your elephant was you're looking for. And then you increase you increase the radius or the density, and everything starts to be connected, and you still hope that you find your big elephant as an isolated component somewhere, and there's a guarantee whatever in which regime you are, you will find this thing infinitely often as a single isolated component of your random graph. Yeah? This means or implies the following. Now, you're in the full space. You don't just cut out a window. Huh? If you're interested in the Betty numbers or in the sequence of Betty numbers, you will find everything with probability 1 infinitely often. And here's the only difference where you have to distinguish between the check complex and the Vietoris-Rips complex, because the check complex clearly it vanishes starting with beta d, because it can be embedded into the d-dimensional space. But it means if you compute the Betty numbers of your components, then you will more or less find everything. Each sequence of Betty numbers which can be realized will be realized infinitely often. And the last question we were interested in was, okay, so assume percolation occurs. You have your giant component, you have some holes, and you have your favorite elephant, and you find it from time to time in one of the holes, somewhere, infinitely often. But can we say something about the giant component, the unbounded component? So can we find this elephant in our component, in the giant component? And this for us was a difficult question, because we want to find this elephant without being disturbed. It could well be you add one point of your giant component to this elephant and everything vanishes and you just have a ball made out of your elephant. Yeah? So you really want to find this elephant as an elephant. And this was the last thing we could prove. If percolation occurs, then you will find your favorite simplicial complex, finite complex, infinitely often, linked via a single edge to your giant component. So the giant component looks somehow like a, say, hedgehog. It has a large number of spikes, and on these spikes there are all these components, these finite complexes you're looking for. And infinitely often with probability 1. So the giant component is really something like a, I don't know, like a beast. It contains everything, if you're interested in. Okay, this was all. Thank you very much. Yeah.
When you say a finite realizable complex, say in the Czech case,
Yes.
you just mean that the nerve is homotopy, a complex that can be realized as a nerve in RD.
Yes, yeah, that's it. Yeah.
Have you tried to count elephants per unit volume as opposed to just counting them? Right.
No, but this is just the expectation. It should be possible, yes. And it's quite clear if you, yes, per unit volume it will be sparse and sparse, yeah. You will not find it. You have a look at your window, and in each window it behaves in a very, very nice way, but there are some windows far away where you find.
Right, there could be some empty windows.
Yeah.
So most of these use statistics that you
Mhm.
mentioned were sort of counting type ones. You know, how many times do you see some particular arrangement or something like that? Can you also do things which could be negative, like this combination minus that combination? Like the number.
Yeah.
So those still things can be converted.
Yes.
And they have all the same properties in
Yeah.
terms of central limit.
Yes and no. See, all things you are thinking about can be solved.
Triangles versus
Yes. You just have to guarantee. See, I mentioned at the very beginning that this L2 question of the kernel and the L2 question of the Poisson U statistic, this is difficult. You have to guarantee that everything is integrable. But counting triangles minus foregons, this is simple, this is clearly integrable, then this will work. And you can even take something like you take the area of a triangle minus the area of a foregon or something like this. Yeah.
More questions? Is anything now in the case where I look at non-Euclidean rows, for example, in some family of non-Euclidean rows?
You mean for the Gilbert graph? Yes, yeah. You can replace the ball by ellipses. The most simple thing is you take cubes, because then both complexes coincide. But you can replace it by any compact convex set, for example, and everything goes through. Yeah.
I thought he meant something else, so I'll ask the question that I thought he was asking. Which is what
Did I
happens
understand?
if you replace Rn by some other homogeneous space.
Yeah, that's also maybe that's very
Yeah, I don't know. Many things, so the Wiener-Ito-Cars expansion, the Maillard calcul and Stein's method, they work nicely in any nice space. The difference is you have to deal with the integration then not over RD, but say over the Grassmann manifold, so I don't know what. This goes through. If you can deal this, investigate these integrals and fix certain integrability conditions, then most things go through. So the use statistic question is on arbitrary spaces. Yeah.
Could you use this approach to ask them maybe something a more delicate question instead of looking for a particular simplest or complex, looking for like like say looking for a triangle with certain angles or
Yeah.
intervals of angles.
This just means you replace f being the indicator function of a triangle by f being the indicator function of a triangle with a certain configuration. This is what you mean.
Yes.
Yeah.
So it's, I mean, I'm only somewhat familiar with the area, but with the like for showing that homology exists, for example, you look for certain triangles or octahedra,
Mm-hmm.
and then, but I'm interested in say persistent homology, so we would
Mm-hmm.
we would want to know that like we'd want to have some control of the angles, or
Yeah.
guarantee that not just you have something at a particular value,
Mhm.
but be something.
But as long as it's a
Yeah.
safe condition.
Yeah.
that's fine.
Okay.
You have maybe a problem to determine the expectation explicitly because the constant then depends somehow on this angle, and if you can really write it down and to integrate this thing. But say the limit theory goes through in the same way.
Okay. Let's thank the speaker once more.